So I thought it might be good today to review a little bit about the periodic table, atomic structure, at least to the first degree, and then see where that leads us into the concept of measuring chemicals and how the mole is a very important unit of measurement and how you use it. So I'm going to start with just picking an arbitrary element. Let's take, I don't know, you guys pick. I always pick me an element that you want to talk about. Just pick one. Doesn't matter.
Iron.
Iron. Very good one. All right, so when I look at iron on the periodic table, you can see to the left the magnified view of that box. The little numbers on the right, don't worry about right now. These are electron shells, and we get into that much later. But the numbers on the left and the letters and symbols and whatnot. Do you know what the 26 stands for? What it's called or what it stands for? And it's okay if you don't. That's fine. No, absolutely no problem. So let me do this just so I can kind of label it for you. Oops, I thought I clicked. I didn't click. All right. Hello. Oh, my computer is really slow today. That's okay. Let's try that again. Screen. Oh, did I move off of it now? Hold on. Well, I got the wrong one. As soon as I went to do it, let's do that again. Print screen. And I hope some of what I'm about to tell you is at least familiar, even if you haven't really studied this that much yet. Pardon me. Okay, so let's go here. Throw the image in place. Eventually. Ooh, the spinning wheel. Okay, then. Sometimes my computer doesn't like to play nice. Okay, there we go. Get rid of some of this junk. And of course, I made a mess of it. How about we do this? Another customer. Perfect. See? That's why it was all getting delayed. Okay, so here we go. Now the numbers you see here, I'm going to label. You might want to sketch this if you want to have it in your notes later. But this here, this first number, is called the atomic number. And it specifically tells me something about atomic structure. It literally tells me the number of protons in the nucleus of that atom. But what's really important about that is that this is literally what defines the element. So any atom that has 26 protons, no matter what else is true, is going to be an atom of iron. And so when you look at the periodic table globally, you'll notice that every element has one of these numbers, right? They all have an atomic number, and they go in order, and they're whole numbers because protons, you can have one or two or three or four, etc. We'll get into what a proton is in just a minute. Now, this number here is actually called the average atomic mass. You might also hear it referred to as the atomic weight, but usually I'll call it the average atomic mass. And the fact that it's referring to an average means that atoms of iron must come in different weights, right? Because if we're averaging them, there must be more than one kind of iron atom. And there's a name for that. We'll see if you know that in a minute. But just to kind of finish up what these symbols mean, this is what is known as the symbol of the element. It's generally one or two letters. And then this, of course, is the name. So that's your basic periodic table geography just to get started. And as I said, this little thing has to do with electron shells, but we're not going to worry about that now. That's a whole other chapter. Um, so let's kind of get a little deeper into this. Now, if I asked you, what are the three basic particles in any atom, what would you tell me? Do you happen to remember them maybe from biology? Well, I gave you one.
Protons, neutrons,
Good.
and electrons.
That's it. And it's important to know their basic properties in a very simple way. So I'm going to give you a little table here. Um, I'm going to give you what's known as the relative charge, because charge is something in physics you'll learn is measured in units of coulombs, but we don't usually get into the physics of atoms as much, so we don't need to know that. We just give it the relative charge. And for protons, each proton carries a charge of +1 in relative sense. And by relative, I mean regardless of what unit I use, that's in contrast to a neutron that carries a 0 charge, which means it's neutral. And then electrons have a charge of -1. So even though we don't have like an exact measure here, what's really important to note is that a proton and an electron have an equal amount of charge, but opposite charges. And the reason why that matters is because charge is a property of things that tells us that they are going to interact through an electrical force. Opposites attract and likes repel, which I'm sure you knew. Um, in terms of the mass, and again, this is a relative measure in atomic mass units. So, and I'll get into this more later. But in terms of the mass of these particles, again, we can measure them in grams, we can measure them in different actual measurement units, but the atomic mass unit just compares them to each other. And so the proton has a relative mass of about 1, and I'm rounding that, it's like a bunch of decimals after, but it doesn't matter that much. The neutron is also about 1, and then the electron is much, much smaller. It's about 1/2000th. So notice this important difference. Even though the electron has the same value of charge as the proton, although it's the opposite, in terms of its weight, its mass, it's much, much, much smaller, right? And then where are they in the atom? That's the last piece for now that we have to kind of understand. Protons and neutrons both are what comprise what's known as the nucleus. And then the electrons are, I could use the term orbitals right now, but let's just say for the sake of understanding visually, they move around the nucleus. So we could use the term orbit, but we're going to learn later that orbit is not quite right. But for now, if you want to just picture the electrons zipping around the nucleus, you can. And what holds them together, of course, is that if we look at, and I'm not going to draw iron because it's a lot of particles, but if we look at something like the hydrogen atom, and I'm going to draw a symbol here, and I'll explain what that means in a minute. This particular hydrogen atom would literally be one proton and then one electron somewhere out here. And for now, a simple view would be that the electron is somehow moving around the proton, and the reason why it doesn't fly away is because their opposite charges mean that they attract each other. And that's essentially the structure of an atom. And again, the physics of that is something we don't have to worry about right now. I just want you to understand how to look at the symbols and translate them into the pieces and where, how the atoms look, essentially, how they're put together. So what you see here is one kind of hydrogen atom. If I was to look at a second hydrogen atom that's a little bit different, it might look like this. And I'm going to draw a picture, and I want to see if you can tell the difference. And then I'm going to bring up a visual thing that we can play with to help you understand this concept a little bit better. But certainly if it's still hydrogen, it can't have more than one proton. What's different about this hydrogen is that there's another particle in the nucleus, and there's still one electron moving around. and the proton still attracts the electron. So what's the primary difference between these two atoms? If they're both hydrogen, what makes them different?
One has two protons and one has both have this one electron. The difference is that one has one proton, one has two.
I don't know about that though, because we said that the number of protons defines the element, right? So there is another particle here, but notice I purposely left the plus sign off. So what do you think I'm trying to represent there instead of a proton? What else could be in the nucleus?
A neutron.
Right. That's the key. So here, both hydrogen atoms each have a proton. They both each have one electron. But in our first case, there wasn't any neutrons in the nucleus. In the second case, there's one. And so chemically, these atoms act the same way. They just have a physical difference in their mass because of the different number of neutrons. Do you know what elements that act like this, or I should say atoms that are related this way, are called? There's a name for this property. And if you don't, that's okay. These are called isotopes. So there's a couple ways we can define this. Well, really one way with a few extra words. It's, let me be careful here. Let me say that isotopes are atoms of the same element and when we say same element, that means the same number of protons. But different mass. And that different mass comes from the fact that there's a different number of neutrons. So this defines a key concept known as isotopes. In fact, the word isotope comes from Greek, which a lot of these words do. Isos means same or equal, and topos means place. And so when you look on the periodic table, there exists multiple versions of hydrogen. In fact, if I go to the isotopes tab on this periodic table website, which is probably the premier periodic table site, it's called ptable.com. I'd bookmark this one or just remember it because it has so much information, it's ridiculous. But if I click on isotopes and I click on hydrogen, you'll notice all this stack of different atoms are different possible versions of hydrogen that could exist. And what they all have in common is they all have one proton. But what's different is they all have different numbers of neutrons. And if I click on almost any element, it's going to be true that you're going to get a stack of possibilities. And the reason why they're called isotopes is because every version of a given element, all the different atoms, all the different isotopes are really represented by that one square. So when you scoop up a sample of iron, and I'm not going to say all these isotopes are found in nature, some of these are just kind of like theoretical, but when you scoop up a handful of iron, you're scooping up a mixture of isotopes of iron that occurs naturally. And we'll get into that analysis a little bit later. But for now, I just want to define the term isotope for you. Now, in the end, you should be able, by understanding the labels of these symbols, to work backwards and forwards between a symbol, a physical representation, and the atomic composition, like what are the parts, what are the protons, electrons, and neutrons. Now, let's label one more thing, and that is this symbol. So this symbol is called isotope notation. and it has a certain pattern here. Notice this is not the same thing as what's written in the periodic table. The periodic table doesn't have room to write every possible isotope. So what they do instead is they give us the natural average of the atomic masses or mass numbers, as I'm about to define. And so this represents that average weight in a natural sample. It would kind of be like if you had a giant bowl of M&Ms, and the M&Ms were a mixture of regular, like plain and peanut M&Ms, and there was a certain percentage of each. Then if you scooped a big sample of it, there'd be a certain average weight, somewhere between the small ones and the big ones. And depending on which there's more of, the weight would, on average, would lean more on one side or the other. So that's kind of what the periodic table shows, but if we want to kind of symbolize any single given isotope, we use this notation. Now here again, there's slightly different definitions. In this notation, the top left corner is where we put something called the mass number. Okay? The mass number is not the same thing as the average atomic mass. The average refers to a group of atoms that are averaged together, right? A sample that has many atoms. But the mass number refers to a single atom. And it literally means, when you tell me the mass number, you're just counting up the number of protons and neutrons. So the mass number is just the protons and neutrons added together. And it's called the mass number because if you look at the table we made earlier, an atom's mass is approximately the sum of its protons and neutrons. I say approximately because these weights are not exactly one, and the electron adds something but so small it can be ignored. So the mass number is pretty close to how heavy the atom is. On the other hand, down here we put what we defined earlier, which is the atomic number. And here we already defined the atomic number as just being how many protons there are. So now you can see that if we were to subtract the two numbers in this arrangement, what we'd be left with is just the number of neutrons. In this case 0, in this case 2 minus 1 is 1. And so this kind of gives us the basic concept of what an isotope is and how these symbols work and what they mean for the structure of the atom. Now let's go back to iron for a moment and let's write the symbols for two different iron isotopes that might exist. For example, we know that for both iron isotopes, one thing is going to be true for sure, and that is they're both going to have 26 down here because that's the atomic number. In terms of the mass number, there might be one isotope at a mass of 56, and there might be another one at a mass of 58. Again, I'm just making up numbers here that are reasonable. What's the difference between these two isotopes? That's the question. How are they different? How are they the same? What do they look like? And to answer that, I just want you to tell me how many protons, oops, sorry, this thing is lagging because I have too many notes on it, I think. I have to start a new page. But anyway, can you tell me, why does that keep happening? It's so bizarre. Protons, electrons, and neutrons are in each. Can you tell me that much? Don't be shy. If you get it wrong, the computer will not explode. How about the first column? Can you answer me of each particle how many there must be? If you're not sure, maybe ask a question about it. And while you're doing that, I'm going to pull up visual that'll help you, and this is one that you can actually do yourself later for practice on this concept. But let's get that going. And while that's loading, let's go back here. So did anybody come up with an idea for any of these particles here?
Is 26 the proton?
Yeah, for both, right? It has to be. Good. So we know that. Now, if you're wondering about the electrons, I didn't really tell you how to figure out the electrons. But there is an assumption here, and it was kind of implied with my first example. You'll notice the protons and the electrons were the same in both of these cases. That's true anytime an atom is neutral. So if I don't tell you that the atom has a net charge, like an overall plus or minus charge, you can always assume the protons and the electrons equal each other. Otherwise, there'd be an overall charge, and I'll show you that in a moment as well. But for now, what that means is that the electrons and the protons have to be equal. So they both are also 26. So then, yeah, go ahead. Good.
30 and 32 for the neutron.
How did you get that?
56 minus 26 and 58 minus.
That's it. That's all I was kind of going for here. So the primary difference between these two different versions of iron is just the number of neutrons, right? But what we should be able to visualize now is that given this symbol, it's representing a single atom that has certain number of these parts, and you should be able to figure out those parts and at least visualize where they go. I'm not going to have you draw something with 56 pieces, but just in general understand the arrangement here. Now, it turns out that in many compounds, and we talk about compounds later, but in many compounds, the iron atom ends up with a positive net charge. So I'm going to make a change on this symbol, and I want to see if you can figure out what that means for the structure of the atom. And just so you know, anytime there's a charge on an atom, it always goes in this corner. And if there's nothing written here, that means implicitly the charge is 0. So to say that an atom is charged, and I'm just going to kind of write this here. Is to say that it is an ion. So the term ion refers to any charged atom, really, or molecule. Molecules can have a net charge as well. But for now, let me just get into the structural piece of this. So I'm going to, let's say in the iron in this first atom is positive 3. Which of these numbers changes, and how does it change? Think about all those same things we said so far, right? How does a neutral atom become a positive atom? What has to happen?
Does the neutron become 33?
No, the neutral wouldn't affect the charge because what is true about the neutron? Look at its charge. Would adding 0 to the charge change it?
Oh, would the proton change then?
But if you change the proton, it's not iron anymore. Right? Like if I added 3 protons to this picture, I would now have, where am I? Here's iron. Oops. 1, 2, 3. That would make me copper, right? I would completely change what element I am if I added protons. Is there any other choice?
Oh, then electrons?
Yeah, what would I do to them in this case?
You add 3.
But if I add 3 negatives, won't it make it more negative?
or 3 positives?
But you can't add positives any because those
Oh,
are the protons. This
then
is this is good. I'm glad you're saying all these things. This is what I want you guys to talk it out. You know what I mean? Keep going, Albert.
would you? I don't know. What would you do with the 3? Do you like change a number with it, or
Yeah. There's only one other way you can make this iron become positive. If you're not allowed to add more positives, meaning
add more
proton,
negatives?
well, that would make it negative, not positive.
Oh, well,
How do you become a more positive person? You lose your negativity. Why can't we take electrons away? See, if I change this from 26 to 23, just think of it like kind of adding positive and negative integers, right? Because if I have positive 26 and only negative 23, then overall I'm going to add up to positive 3, right? So here's one of the tricks about ions. Atoms can gain or lose electrons. See, that's the key to all of chemistry right there. The fact that it's the electrons that are on the outer part of the atom that are held by the nucleus's attraction for it, but are able to be kind of flicked off or added on and moved around. That's really what chemistry is all about. It's about that dance. And so this is just one tiny glimpse into that dance. It's a very complicated thing, but every chemical process involves the movement of electrons in one form or another, like their shifting or their transfer or their exchange with other particles, whatever. But that's really at the heart of all of chemistry, and that's why the atom is kind of like, you know, the letters of chemistry, and the elements on the periodic table is the alphabet. And you're going to start learning the rules on how to make compounds, which are like words, and eventually chemical reactions, which are sentences, and then understand underneath why that happens and how it happens. So let's take a look at what we've done so far. And I'm going to go to the summer packet for a moment and show you kind of what I just zeroed in on without telling you. And let's see. So if I'm looking at the summer packet, I just kind of chunked my way down to here. And I'm going to copy this one section. This is Learning Target 7 and really questions 10 and 11. I'm going to copy this piece so I can write on it. And then let's kind of do this piece together and see where we're at. I'll grab this whole chunk. Okay, what do we got here? Man, this thing is running slow today. All right, here we go. So in this first part, it says to figure out the number of protons, electrons, and neutrons in each of these atoms. So let me just pluck a couple out here and we can go through them. So when you have uranium-235, here's your mass number, here's your atomic number, and your charge is implicitly 0. Can you tell me for this atom how many protons, electrons, and neutrons it has? First, tell me the protons. Don't be afraid to use your voice. Anyone? Protons?
92.
Correct. Electrons?
92.
Correct. And the neutrons?
Wait. 235 minus 92, which is 143.
And that's the pieces of that atom where the protons and neutrons are chunked into the nucleus, and then the electrons are flittering about outside at relatively great distances. Okay, so that's what these kind of problems are, and so you should be able to do that now. The table is very similar. In the table part, we're going to do almost the same thing, it's just laid out a little differently. So I'm going to start, and you need a periodic table, obviously, to complete this, so we'll kind of bounce back and forth. But they're telling me gallium. Okay, let me kind of do a split screen here. Whoop. We have some people falling in and out a little bit. All right, welcome back. That's okay, I know that happens, the old internet stuff, right? But let me kind of zoom into gallium here. Okay, so the reason I need to know, okay, I got to turn off the isotope thing, it's getting on my nerves now. There we go. Gallium, well, I guess I got to be on at least properties. Okay, so the one thing I can tell from gallium, from the periodic table right away, is its atomic number is 31, right here. And by definition, the atomic number is equal to the number of protons, so that's 31. The neutrons is based on the mass number minus the atomic number. So that's 70 minus 31, which is 39. Because there's nothing to tell me that it has any net charge, that it's an ion, right? There's no charge shown anywhere. I know that for a neutral atoms, the protons equals the electrons. And now to write the symbol properly, I look at gallium as just Ga. I see that its mass number 70 goes up here, and its atomic number goes down here. Now I'll write 0 explicitly up here just to really emphasize that there's no charge, but you don't have to write the 0. Let's look at the next one together, and then maybe I'll have you guys try the last two on your own just to see if you're getting this. So the next one, we're going backwards. We're starting from a phosphorus atom that has a -3 charge. We have an atomic number and a mass number. So right away, as soon as I see that this number down here is 15, I know that's the atomic number and the number of protons. Now, my neutrons I can find by the difference from the mass number, which is 31, and then I subtract the 15, and that gives me 16 neutrons. Now, I just happen to know the periodic table because I've been teaching it for 90 million years. But on the periodic table, you can find the name. It's phosphorus. And then for the number of electrons, this is just the trickiest part. Because the net charge is -3, that means there has to be 3 more negatives than positives. Well, my protons are my positives, my neutrons are neutral, and my electrons are my negatives. The only way this could work and still be phosphorus is if I have 3 more electrons than protons. And since the protons are 15, the electrons here have to be 18. Notice they're not equal because we have an overall negative charge. Any questions on that before I turn you loose on the next two and see if you can figure them out? I'll zoom in so you can see a little bit better. One side note, when you see an element name with the number in the name like that, that's always the mass number. So like this one is uranium 235. This one is carbon 13. So when you hear somebody say an element name with a number, they're telling you the mass number. I just thought you needed to know that for this next example. So you guys take a few minutes and try these two. And let's kind of compare after you're done, okay? I'm going to pause my sound here for a moment and let you guys work. And then if you have questions, just ask.
Wait, does strontium have any like atomic weight, or like in the second one?
Well, that's why this is why I just explained about the how the
Oh,
name. Yeah, that's the 80, right?
oh, okay.
hmm You need any more time? Well, let's take a look. Um, let's just go through the answers and then I'll see if there's any questions. So what about, let's just kind of go across this first box, row, I should say. Strontium 80, what's the mass number?
80.
Yeah. What about the atomic number? Where do we find that? Go on the periodic table and look for the symbol or the name of strontium. It's down here. So the atomic number is 38, which is the protons. Neutrons should be the difference, so that would be 42. This doesn't show a charge, so it should be also 38 electrons. And then to write it in the isotope notation, mass number top, atomic number on the bottom. And then the last one is called manganese. You don't have to specifically put the mass number in the name. We just did that to throw that in there so you'd know when you saw it what it meant. But you can see from the symbols there should be 25. Oops, let's start with the mass number. 55 for the mass number. 25 is the atomic number, which is equal to the protons. This has a positive 2 charge. And because of that, there's 2 electrons less than protons. We have less negative charge. So we take 2 away from 25 for the electrons. And then the difference is just the number of neutrons. So I'll pause there and see if you have any questions. If you got any of them wrong or not sure how I got them. And while you're thinking about that, here is, I can put this link in the chat for you if you're interested. Where is it? But this is one of the, oh yeah, go ahead.
So I'm kind of confused about like the charges and what do you do when you have a charge?
Sure. So here's what I want you to think about, and I think I'll use this visual to help you see it. So if you go into this setup here, it will let you actually build the atom. The only downside to this is it only gives you like this many particles. You can't make really big atoms, but if you play with this enough, you'll get the idea. So let's start by throwing some protons and neutrons in there, right? So right now I have 3 protons and 3 neutrons. You can see them up here. You can see right now the mass number is 6 because we just add those up. You'll also notice that the net charge is positive 3 because I don't have any negative charges in here yet. So what do I do if I want to bring the positive charge down? I start adding electrons in. And once I have the electrons equal to the protons, it's neutral. So when you start from there, you can see how this all balances out. But if I want to make the ion negative, I put more electrons in. If I want to make it more positive, I pull more electrons out. Notice it's only the electrons that I get to manipulate, because as soon as I throw in a different number of protons, I change the element. So adding neutrons changes the mass, but it doesn't change the charge, and it doesn't change the element. It makes a different isotope. Changing the protons changes the mass, but it also changes what element I am. Changing electrons doesn't really change the mass, but it changes the charge and leads us to having ions. Does that help, or is there...
Yeah. So like when it's a positive charge, you're adding more electrons.
No, careful. Watch what I do to get a positive charge. Ready? Right now it's neutral, right?
Yeah.
The only way to make this more positive and still be lithium is to take the negative away.
Oh.
If I want to make it more negative, I add a new electron. You see how I'm tipping that back and forth, but it still says lithium?
Yeah.
If I wanted to make positive lithium by adding another proton, well, it would be positive, but it's not lithium anymore. I totally changed what element it is by changing the protons. So let's go the other way. Let's say that I wanted to build, here, I'll write the element and then we'll see how would we put it together, right? So let's do, because I want to make sure I have enough atoms to do this. So let's say we wanted to build, just making sure I have enough atoms. Let's do oxygen with a mass number of 18 and a charge of -2. So let's say this is what I want to build, right? So in order for me to build oxygen, I have to put 8 protons. 1, 2, 3, 4, 5. You'll notice I'm just going across the periodic table. 6, 7, 8. So now I have oxygen just based on the protons. Now you can see that this specifically needs 10 neutrons to be the isotope that I made. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's my nucleus, right? If you look at the mass number in this little box, it weighs 18, just like I wanted it to. But right now, I have 8 plus charges that are not accounted for, right? They're not balanced out. So I need to get to a -2 charge. Well, if I put in 1, 2, 3, 4, 5, 6, 7, 8 electrons, that gets me even. So now I have a neutral oxygen atom. But this needs to be -2, so 2 extra electrons are thrown in. And now you can see I have a surplus of 2 electrons, which builds this specific, not only this specific atom, but this specific ion. So it has all the right parts now to represent this symbol. Does that help? Or?
Yeah, that helps.
So I'm only going to cover one more piece of this today. I don't want to go into the mole thing because I think it would be too much information for one session. But I think we're doing good so far. So what I would suggest, like I said, I sent you this link in the chat, but it takes you through this. It lets you kind of play around with it this way, so you can watch the symbol notation as you build atoms, and you can see what numbers are changing based on what you're adding, right? And then finally, there's a game version where you just it just throws you practice questions, and you can just test yourself. So in honors, we do this as like a little mini lab activity where I have the students go through this packet with this simulation. I'm not going to make you do all that, but I'm just showing you this is good if you need to practice this concept more. Now, I think there's another PhET that will be useful to us here. Let's see if we can. To do the last concept that's connected to what we've done so far. Let's go to, probably just be easier to Google search it, but I do want to find, I think they have one for average atomic, here we are. Perfect. All right, let's take a look at this one. So we already talked about the concept of the isotope, but we have not talked about the concept of abundance in nature. So it turns out there's a machine, and we talk about this more in class after we get back, and so I'm not going to get into the graphs on the machine yet, but let's at least talk about the concept. But there is a machine that can separate isotopes and count them. And so we can actually take natural samples of any element, and more than just elements, but for now, let's just focus on elements. But you can take a natural sample of an element, and you can separate it into its isotopes and figure out the relative abundance. Again, I'll go back to my M&M's mixture. If you had peanut M&Ms and regular M&Ms mixed in a bowl, and I said, well, tell me what's the percent of each? Well, you'd know what to do. You would just spill it all out, count the total number, count how many are peanut M&Ms, count how many are regular M&Ms, and you could find the percentages, no problem. And that's because, these are large enough objects to count with your eyes, and there's not like a billion of them, so it's not going to take you the rest of your life. But even in a simple 1 gram sample of hydrogen, there's like 600 trillion atoms. So counting it out that way is not very efficient. In any case, we have an instrument that can actually do this kind of process, and we get these percentages. So if we take hydrogen 1, which is the one with just 1 proton and no neutron, almost all the hydrogen in the world that we test is this type. When I add a neutron to it, you'll notice that I get something called deuterium, or hydrogen 2. And it's a very, 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 very tiny fraction of naturally occurring hydrogen. And if we throw a third neutron in, which is called tritium, and you can notice it's unstable, which is a whole other story. When they say trace, that means it's so small you basically barely detect it at all. So it has almost no bearing on the average atomic weight. But here's the question. If the two major isotopes of hydrogen are 1 and 2, why is the average not 1.5? Why isn't the average weight, like there's the kind that weighs 1 and there's the kind that weighs 2? Why isn't the average 1.5? Any thoughts? In fact, let's put the average. There's the average. That's when you take a natural sample, that's the average atomic weight. Why is that? That's such a funky looking thing. Why isn't it 1.5? Let's see if we can figure it out conceptually first, then I'll look at how to do it mathematically. We don't need this. I'm just going to close some windows here because it's starting to get, like I said, slow. So let's think of it this way. And again, I always want to make sure you're understanding the idea, not just saying, oh, I just do this. If you're going through my class and saying, oh, I just do this, then you're doing it wrong. If you can't say why it works or what it means, you're not learning to the expectation that I want you to. So let's take one object and say it weighs 1 unit. And let's take a second object and let's say it weighs 2 units. What's the average weight? Well, the average is equal to 1.5, right? Because there's one of each. I'd add up the total, and I divide by how many there are. 3 over 2 is 1.5. Easy peasy, isn't it? But what if, oh, and by the way, just so we understand, if there's only 2 atoms in the pile, doesn't that mean 50% of them are this kind? And the other 50% are this kind? So how does that change? Actually, let me put the average up here just so I can keep working these problems until you get the idea. How do the numbers change if I suddenly added a third atom? Is the average still the same? Just think about how you find averages. Well, now there's 3 atoms, so that changes this denominator to 3. Now there's a total mass of 1 plus 1 plus 2. So now my average is 4/3, which is 1 1/3. Why did the average go down? It's the same kind of atoms. And another thing that changed, of course, is we no longer have a 50-50 mix. This is 2/3, so about 67% are this kind. And this is 1/3, so about 33% are this kind. And what I hope you can see is that this isn't the simple average, it's what's known as a weighted average, because it accounts for how many of each type are in the mix. So you'll notice that if I kept adding more and more 1s, so let's add another 1, well, how do the numbers change now? Well, now we added another 1. Now there's 4 total atoms. Now it's 1, 2, 3, 4, 5 over 4, which is 1.25. So you'll notice that the more and more of these 1s we add, the lower the average gets, meaning it gets closer and closer to 1. Now when we go back to this, it starts to make more sense. When I look at the percentage of mass 1 hydrogen atoms Almost all of them, 99.9%, are that kind. When I look at the next possible hydrogen atom or isotope, only a tiny fraction of them are this heavier type. So even though these atoms are twice as heavy as the last, there's so few of them they don't add much to the average. And that's the essence of what we're looking at when we look at the periodic table's average atomic weights. We're looking at how the natural distribution of isotopes in that mixture add weight to the average. And that, based on that, we can kind of treat, for our purposes, every atom as if it had the average atomic weight. And you'll see why that's important later, because that allows us to count huge numbers of atoms within a second. We can count literally cajillions of atoms within literally seconds, because we can just weigh the sample and relate the weight of the sample to the weight of each particle and then count the particles. But again, I'm going way ahead of myself here. I'm just trying to give you a reason why we're looking at this. So at this point, if we go back to this concept, and instead of just keep doing this over and over, let's look at what happens if we look at a mixture. So I'm going to kind of do what I did on paper by just throwing them into the pot here. So you throw in one of these, 100% of the atoms have the same mass as this. Throw in another one, still 100%, right? Because they're all the same. Now start throwing these in, and all of a sudden, the average shifts. Throw another one, throw another one, throw another one. See, now it's 50-50, so it falls in between. Now again, they're accounting for the fact that the hydrogen atom is not exactly mass of 1. That's why it's a little bit off. But I'm just trying to show you the role of the composition, like the percentages. Let's look at a different element. Let's say carbon. Most carbon is carbon-12. Throw in some carbon-13, and you start to shift the average. So depending on the distribution, okay? Now, if you want to look at how nature looks for any of these elements, this shows you the relative mixture of a sample of naturally occurring carbon based on the isotopes. So most of it's carbon-12, and there's just a little smattering of carbon-13 that raises the average. There's some other trace elements as well, but for the most part, this gives you the reason why the average atomic weight is so close to 12. What about nitrogen? Again, nitrogen is almost all one type, nitrogen-14, and there's a smattering of 15 that brings the average slightly different. Let's look at one that I think is more interesting, like chlorine. You'll notice in chlorine, we have a significantly closer, or not closer, but a significantly higher number of different isotopes. It's not like 99% and 1%, right? So here we actually get an interesting situation. So it turns out that the major mixture of naturally occurring chlorine atoms is about 75-25. 75% of these chlorine-35 atoms, and about 25, a little less than 25% of the chlorine-37. I'm going to grab this, and I want to show you a simple calculation we could do to find the average atomic weight, because that's kind of a kind of problem you have to learn how to do. So like if I took those numbers, that data, and again, we get into this more as a class when the year starts, but at least to have this basic understanding is important. If we take this piece, oh, I forgot to cut out the garbage, as they say. Let's just take, I just need this part actually. That's the one I needed. All right. So I'm going to show you a real easy way to calculate this. So there are the two parts that you need to know. This percent composition. You might also see it called the relative abundance, which is just abundance, which is just the percentages of each isotope in the mixture. So it's kind of like saying, all right, if I had 100 atoms, and obviously it's not literally 100 atoms, but because we're working in percentages, that makes the math conceptually easier. But if I had 100 atoms, 75.76 of them would contribute 35 atomic mass units of weight. Again, that AMU is just a relative mass unit. Then I'd have to add the weight contributed by the other 24.24 atoms, which are contributing 37 atomic mass units. And so this would represent the total mass, right? They came from all of it. But if I want the average, I have to divide by how many atoms, which I assumed for the purposes of this calculation is 100 atoms. So I'm just going to divide this by 100. And if you do the calculation, actually punch the numbers into a calculator, which I'm going to do, 75.76 times 35 plus 24.24 times 37, and divide that by 100, I get about 35.48. So their numbers are not exact, but it's close enough to show the method. So the average atomic mass would come out to about 35.48-ish, right? Pretty close. The bottom line is the method. Now, do we always have to put the 100 in? We can actually pull the 100 out and simplify the calculation even further. Just take the abundance and turn it right into a decimal, and you're taking care of the 100 right away. The reason I say to be careful with this is sometimes students get confused. If you have like 0.17%, if you want to turn that into just the raw decimal, you still have to move the decimal point 2 to the left. So even though it's already a decimal, you still need 2 more places, right? So just be careful of that. But other than that, we could have found this average really quickly by just taking each abundance as its fraction or decimal, 0.7576, and then just multiplied it by the mass number of that specific isotope, and just add those terms up. So what you'll notice I'm doing is I'm already pulling the 100 out. That's all. That's how the average atomic mass is calculated from these abundances. And what's cool about this is that now we can treat every atom as if it has that average weight. So when we're taking a big sample of these atoms, we kind of pretend they all have that average weight. And that's why when we look on the periodic table, we can report just the average atomic mass and know that, yes, there's a distribution of isotopes. But for most of the chemistry work we want to do, that doesn't really matter, because what's going to matter to us is that if we want to count these atoms, then we need to know the average weight of one. It would kind of be like, do you ever do like one of those jelly bean counting contests? And the jelly beans aren't identical, but they're pretty similar. But they're going to be some heavier and some lighter. But if you knew the average weight of a jelly bean and then weighed all the jelly beans, you could figure out pretty accurately how many were in the mix. And that's what we're going to learn how to do with this newfound knowledge on atomic structure and atomic weight. So we're going to learn how to translate between how much a sample of matter weighs and how many pieces are in that sample, because that becomes really important. So that's kind of the end of this presentation, as it were, in terms of lessons. Just as a quick follow up here. What we just did in terms of the summer packet, skip down here, is, did I go too far? Somewhere around here. Or do we not cover it in the summer packet? I thought we did. Maybe, no, isotopes, no, or does it come later? Let's see, I think it may come later on the packet. Ah, here, okay. So I just did basically this problem here. Calculate the average atomic mass of an isotope using abundances, okay? So it looks like I'm skipping around, but this kind of connected so nicely to what we just did with atomic structure. We covered it here. And then next time I'll start talking about molar mass, the mole concept, and those conversions. I'm going to stop the recording now.